Second. So hi, good afternoon. This 10th live session. Okay. So today we are going to discuss about Riemann sum and Riemann integration. So first, let's start with basic definitions, and then gradually we will go to some problems. Okay. I hope everybody know the definitions of Riemann integration. At least we should have the basic knowledge. Okay. So. uh, so I'm not going to define each and every definition. So today we're only going to see some important definitions so that we can start with some problems. Okay. So the first thing is that suppose f is a map from closed interval AB to R, then apart sum and let P belongs to P is a partition of AB. Then the upper sum of A with respect to the partition P, known as UPF, is equal to summation MR into XR minus 1, R is equal to 1 to N, where MR is equal to supremum of XR minus 1 Fx. Okay. And similarly, lower sum of F with respect to P defined as LPF summation small mr xr minus 1 r is equal to 1 to it. And by the way, P is the partition. So P is equal to A is equal to x0 less than x1 less than xn is equal to P. This n, okay. So r equal to 1 to n this, and small mr is equal to infimum of fx x belongs to xr comma xr minus 1. Okay. Function f is said to be Riemann integrable if UPF, sorry, if the upper integral of f is same as the lower integral of f. By the way, just for sake of recall, this is nothing but the infimum of UPF, or P varies of the partition AB, supremum of, and this integration AB bar, supremum of LPF P belongs to partition AB. Okay. So yeah. The next thing comes is that there is some important observation. Yeah. And if the function is Riemann integrable, then this common value is denoted as integration a to the f. Okay. Yeah, that's it. So let's get started with an easy example. So um, let's consider AB closed boundary interval in R, and let's C belongs to R be fixed. If X is equal to C, that is a constant, man. Show F is Riemann integral. How do it? Can you see the screen? Can you see the screen? Am I audible? Can you please tell me? Can you see the screen and am I audible? So today we are discussing about the Riemann integration. First, we have give the definition of the when a function is Riemann integrable. Then we are this is the first problem. We are trying to show that the constant map is Riemann integrable or not. Okay. So if x is C, we need to check that is Riemann integrable or not. Start with the definition. Let P choose a partition. Let P be a partition of A. Let P is equal to A is equal to x0 less than x1 less than xn is equal to B. So then, what is UPF? UPF is equal to what? So I mean, for the consider the partition XR minus 1 comma XR. For this portion, small capital M order in supremum is equal to C because function is constant and small M are also C. So anyway, UPF is equal to summation R is equal to 1 to NC XR minus XR minus. So this is C into B minus A. And similarly, LPA we can easily use C into B minus A. Okay. So clearly UPF is equal to C into B minus A is equal to LPF. And its whole on partition belongs all partition of A. So this implies what? This implies lower integral of F is equal to C into B minus A is the upper integral of F. So this implies F integrable. Integral means Riemann integrable. And integration A to B F is equal to C into B minus A. Okay. So now consider the following problem. The ABF function defined on 0 to R, 0 1 to R defined by fx is equal to 1, a rational number is equal to 0 if x is irrational. So if it's not integrable, or so how to do it? So basically, so the pain test we need to show upper integral not equal to the lower integral. Okay, but how to do it? So okay. So since we need to show upper integral not a lower integral, so choose the partition P. Choose any partition P of B. Okay. Partition P. Okay. Recall that set of rationals and set of irrationals are tangent. So in xr, xr minus 1, we will get rationals and irrational. So what is the UPF? I mean, first of all, what is capital M? Capital M will be 1, and what about small m equal to 0, right? So so UPF, it will be what? It will be summation r equal to 1 to 1 xr minus 1. This will be b minus a, which is 1 minus the regular part. But what about LPF? LPF is equal to summation r is equal to 1 to n 0 xr minus x minus 0. So anyway, the not equal to the opposite. So if not integral. Oh. So yeah. So now, mm, okay. Now the point is that we can find the integration of some easy functions using the definition, but practically, in order to find the integration of some complex on some functions like exponential or log, this is very difficult using the definition. So for that, we have two theorems and we need to use those theorems. So so I'm going to stick to the theorem without the proof. I hope Sarah has given this proof in the class, okay? And then we will see some applications of that theorem, okay? So let's find the theorem first. So the statement of the theorem. So by the way, first let me introduce the normal partition in case some of you don't know it. P is a partition of AB. Let P is equal to A is equal to x0, let x1 set is equal to B. Then the norm of P is defined as x1 minus x0, x2 minus x1 dollar, xn minus xn minus. So you know the norm of partition. Now we have the following theorem. This one, suppose f is a function a to 1, and let Pn be a sequence of partition such that norm Pn goes to 0 as n tending to infinite. Okay. Then upper sum will be limit n tending to infinity UPNF, and the lower sum limit n tending to LPN. Okay. So this theory is useful in order to find the upper infinity and the lower infinity. So okay, so using this, first let's evaluate the integration of identity to application. So application of theorem. So function define fx equal to x belongs to x. Then let us find integration 80. So we all know that the value will be it's a small line, right? So, but we are going to prove it using the above theorem. So, okay, for the sake of calculation, to make it easier, we are putting the functions 0 and 1. Then later, using change of variable, we can do it. So, to the partition Pn, 0, n, 2 by n minus 1 by n, which is nothing but n by n. So, it's a partition and what is non-Pn? Non-Pn is equal to 1 by. Okay. Now, find the UPF. UPF, the opposite. So, this will be what? Summation r is equal to 1 to n mr xr minus xr. So, this will be r equal to 1 to n r by n of r by n minus r. So, this is summation r is equal to 1 to n r by n by 1 by. Okay. 1 by n square summation r equal to 1 to n r. Summation 1 by n square r n into n plus 1 by 2. So n plus 1 by 2n. So this according to the limit n tending to infinity UPN, and this is what limit n tending to infinity when, so by calculation it will be what 1 by 2. Okay. And now find the lower now find the L in F. This will be what summation r is equal to 1 to n small m x r minus 2. So small mr into, so sorry, the what is the small m? So we r to the 1 to n r minus 1 by n r by n minus r. This will be what summation r is equal to 1 to n r minus 1 minus 1. C is 1 by n square is equal to 0 plus 1 plus n minus 1. So this will be what? Will be 1 by n square n minus 1 by 2. This will be what? This will be minus bit 12. So the lower sum f is equal to limit n tending to infinity L DNF. This will be what? This will be limit n tending to infinity n minus 1 by 2n. So this half. So what we have, so the upper integral is half and the lower integral half. So x goes to x is integrable on 0 1, and the value of this integration, if we call it f, the value of the integration is half. Okay. So this is an application of that theorem, namely this one. And anyway, similar by similar process, we can show that integration into the f is equal to b square minus a square by 2 by similar method. So now, once again. Okay. So now let's evaluate the integration of the exponential using this process. Okay. Wait, I shall be back within 2 minutes. Okay. Once. So, so once the function f(x) is equal to x, and choose the interval x belongs to interval integration a to b f(x) x. Well, so how do we? So the same method. So let Pn be a partition of AB with norm Pn is equal to 1 by n. Okay. Once. H is equal to then Pn will be what? Pn will be a my a plus h, comma a plus h, comma a plus n minus 1 into h, comma a plus n h, which is nothing but b. Here we need to check the Pn to be 3 minus a by n. So then supremum, then MR will be what? MR will be by definition supremum of x belongs to a plus r minus 1 comma h comma a plus rh. What is it will be increasing function? So this will be what? This will be e to the power a plus rh. Similarly, small a more equal to e to the power a plus r minus 1 h. So now, what is the UPNF? UPNF is equal to small h into e to the power a plus h plus e to the power a plus 2h plus e to the power a plus h. This will be equal to h into e to the power a plus h into e to the power h minus 1 by e to the power h minus, which is basically the multiple property. Calculation is getting what? H e to the power a plus h into e to the power e minus a minus 1 by e to the power h minus. So this will be what? This will be h e to the power h by e to the power h minus 1 into e to the power b. And what is LPNF? LPNF is equal to h into e to the power a plus e to the power a plus h plus e to the power a plus n minus 1 h. So this will be h e to the power a e to the power nh minus 1 by e to the power h minus the h e to the power a e to the power v minus a minus 1 by e to the power h minus. This is h by e to the power h minus 1 into e to the power v minus e to the power a. Okay. So now let's calculate the limit. Now upper sum of f is equal to limit n tending to infinity. UPNF this will be equal to limit n tending to infinity. Now point is that since the h is equal to b minus a by n, so n tends to infinity if and all if h goes to 0. Okay. So we are going to use this technique here. So limit h equals to 0, h to the power h by e to the power h minus 1 e to the power b minus e to the power n. So this is by calculation to what? E to the power b minus e to the power n. And we can see that this is same as limit n tending to infinity after calculation into L and f. So this is nothing but the lower sum of f. So it can e to the power x and x is equal to e to the power b minus e to the power. So f is done. So in this process, we can do integrate onto some complex function also. Now, okay. So what so now let's consider the following problem. Function f defined on closed interval 0 1 by fx is equal to x belongs to closed 0 intersection q is equal to 0. close 0 1 minus q. Okay. So the questions are find in lower integral and upper integral and deduce if not integrable on 0 1. Okay. How to do it? So going to use the last theorem that there where we can find UPF and APN sequential criteria. Okay. So let's solve it. Now, so that with bounded in 0 1. So consider partition, sorry, here A equal to 0, B is equal to 1. Okay. So consider the partition Pn is equal to 0, 1 by n, 2 by n minus 1 by n, n by n which is 1. So the norm Pn goes to 0 as n tending to infinity. What is AMR? AMR will be what? Supremum of x belongs to r minus 1 by n comma r by n of this function fx. So anyway, this will be equal to small r by n, and small amount is equal to the infimum r minus 1 by n comma r by n fx. So what is UPNF? So UPNF will be 1 by n into 1 by n, 2 by n plus dot 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 n by n. This will be n plus 1 by 2n. And what will be the LPNF? LPNF will be 0 since m equal to 0 for all n. So upper integral of f is equal to limit n into n plus 1 by 12. This will be half, which is not equal to 0, which is equal to the lower integral of f. Hence, so f not integrable on 0 1. Yeah, that's what this is what we want to check. Okay. So now, once. Now, okay, so consider the following problem. Data function f. So, I mean, it's a problem, actually, it's a theorem. There are some important theorems that we are going to state, which will tell directly that some functions, if given satisfy some condition, it will be integral or not. Okay. So I mean, so I'm going to study the theorem without proof. Okay. So some theorems. Function is integral. 'Continuous map is always integral. And functions having finite number of discontinuities is integral. Sorry. Okay, these are some important theorems. Now, there are some important theorems which are looks almost obvious from the usual integration. But you know, this is a theorem. One can find it any textbook. I'm going to study this theorem without the proof. If AB2 are EAB2 are, then A plus G is Riemann integral, and integration AB A plus G is equal to integration A to B F plus integration A to B G. Okay, this is the one theorem. And the next theorem is that if when we do on be integrable on AB and C belongs to R, then CF is integrable on AB, and integration A to B CF is equal to C integration A to BF. And the theorem is if Riemann integral implies mod F Riemann integral. F G both integral implies that multiplication is integral. Okay. So these are some important theorems. Now, Okay, let's look at some applications of this theorem. Okay, I shall be back within 3 4 minutes. Okay. So, consider the following problem. So, let's look at the box function. Fx equal to third bracket x and 0 3. F is hmm. It is 0 3. So now observe that if x is equal to 0, when 0 less than x less than 2. So if x equal to 1, 1 less than equal to less than 2. If x is equal to 2, 2 less than equal to x less than 3. Equal to 3, x equal to 3. F is bounded on 0, 3. If continuous on 0, 3, except for point 1, 2, 3. If integrable on 0. So basically here what we are seeing that if it's continuous on 0 except for finite number of points, so it's integrable. And what is the value of the integration? So well, so in this portion, let us call this as phi 1, phi 2, phi 3. Then value of the integration 0 to 3 f, 0 integration 0 to 1 f, so 0 to 1 phi 1 plus 1 to 2 phi 2 plus 2 to 2 phi 3. So this will be 0 to 1, 0, 1 to 2, 1, 2 to 3, 2. So 0 plus 2 minus 1 plus 2 into 3 minus 2. This will be 3. So value of the integration is okay. And mind that also if you look at the box function, it will be what? This will be this 0, 1, 2, 3. So this total area is actually 3. Okay, so the similar integration somehow gives similar result to the usual integration, but obviously there is some condition. Okay, so we shall discuss it. So consider another problem. I shall get back solving problem. Construct function f is equal to 1 by n one when x lies within infinity. That f integral evaluate integral 0 to 1 f. Now exactly process a similar sum. So first here we will look at the f in each smallest term. So okay, fx is equal to 1 when half less than x less than 0. Fx is equal to half when one third less than x less than 0. Sorry, one third when one fourth less than x less than 0 when x equal to 0. Clearly, if we continuous except half, one third, one fourth, that's it. Has only has only finitely many limit points. So f is integrable on 0, okay. So like similarly, so here we can choose it 5 1, 5 2, 5 3 dot dot dot. Okay. So first of all, integration 0 to 1 f, 0 integration up to 1 5 1, 132 5 2, 4 5 3 plus dot dot dot. But how to calculate it? Okay. So first separately calculate the integration up to 1 5. This will be what? This will be integration 1 third to 1 5. Half into half minus 1 third. This will be, I mean, keep it as it is. And the integration 1 by n plus 1 to 1 by n phi n. 1 by n into 1 by n minus 1 by n plus 1. Then integration 0 to 1 f is equal to limit n into 1 minus 1 by half plus half into half minus 1 third plus 1 by n into 1 by n minus n plus. So this will be equal to what? Limit n into infinity 1 by 1 square square 1 by n square minus 1 by 1 dot 1 by 2 dot 3 plus 1 by n dot n plus 1. So limit n into infinity 1 half l square 1 by n square minus 1 minus 1 by. So this will be what? This will be pi square by 6 minus 1, since 1 by 1 square plus 1 by n square pi square by 6, and divided into 1 minus 1 minus over 12. So this integration is actually 1. So these are some of the problems that I think we need to solve in the first session. So let me find some other problems. Okay, guys, I'm back. Okay, so let us okay, so the main thing now is that the fundamental theorem of integration, Riemann integration. So by which we can do the integration very easily. Okay. when a b to r be integrable. This statement, okay. If it's a function of a b to r which is integrable, and if has an antiderivative, then antiderivative on a b, then the integration a to b f is nothing but 5b minus 5. Okay. So this is a theorem by which we can do the integration very easily. So this is a fundamental theorem. There are only two conditions. One is integrable and the second antiderivative. Okay. So let's solve a tricky problem using it. F is a function defined on minus 2 by fx is equal to 3x square cos pi by x square plus 2 pi sin pi by x square x not equal to 0 and 0x equal to 0. So f is integrable to evaluate integration minus f to f. So you can define a function phi x is equal to x cubed cos pi x square x not equal to 0, 0 is phi is antiderivative of f. So integration minus to f is equal to what? Phi 2 minus phi minus. Now what is phi 2? What is phi 2? Phi 2 is what? Phi 2 is Okay, I shall be back within some minutes. So, solve the integration. So, observe that here we need the L'Hopital structure. So, we are going to L'Hopital's rule. So, there is 0 by 0 form. So, this will what? So, this will be derivative of the numerator by derivative of the denominator. Okay. So, 2x integration, yeah. So, 2x e to the power root over 1 plus x square. by 2x. Limit x goes to 0, 3 to the power root over 1 plus x, which is nothing but 2. Okay. Next problem is let f be continuous minus x to x f to integration 0 to x f dt. Then show that um, f is an even function. How to do it? So c is given x equals to minus x to x f dt. To integration x f dt. Okay. This implies integration this is what? This is minus x to 0 f into 0 to x f is equal to integration 0 to x f. Okay. So this implies integration minus x to x 0 is equal to 0 to x f. And this thing is going to minus of 0 to minus x f. So integration 0 to x f is equal to minus integration 0 to x minus 0 to minus x f. Okay. Now the derivative. So this fx is equal to minus of f minus x into minus 1, which is f minus x. So by doing the derivative. So the next problem, so let me find the next problem. So consider the following problem. Yeah. So consider this problem. So if the continuous function and if is greater than or equal to 0 and if not equal to 0, x not equal to 0. Now given if x whole square is equal to 2 integration 0 to f, then show fx equal to x for all equal. Here we need to do derivative again. Now by doing derivative, sides get to fx f dash x is equal to fx. And that's what is implies f dash x equal to 1. So this implies what? This implies fx equal to x plus k for some constant or some k. Mean. Now this equation gives f0 equal to 0. So k equal to 0. So fx equal to x. And so basically in this term problem, whenever relation is given, just you need to do the derivative on both sides, and by using the conditions given condition somehow we can find that we can easily get the answer. Okay, so that's the point here. So yeah, next problem. Sorry. If the continuous and integration minus x to x infinity equal to 0. Proof if how to do it. Since minus, so what this is minus x to 0 f plus 0 to f. Now this is what the minus of 0 to minus xf 0 to xf equal to 0. This implies Integration 0 to xf is equal to integration 0 to minus x. This implies what? This implies fx is equal to f minus x into minus 1. So it is minus x. So this is f minus x is equal to f. So if an odd. So this is what we want to show. So now okay. So I should get back after 2 3 minutes. So yeah, consider the following problem. So sorry, I will be late because I find some problems. So yeah, so evaluate limit x goes to sorry. evaluate limit equals to 0 integration 0 to x squared sine root t dt by x cube. Sorry, let me write in a question. So evaluate the limit equals to integration 0 to x squared t dt x cube. So this is what, so now it is a 0 by 0 form. Now this is 0 by 0 obviously. So we are going to now using the Taylor's theorem. So it will be what? It will be sine x 2 by 3 x squared. This will be what? 2 by 3 limit x goes to 0. Sine x by 1 is equal to 2 by 3. Okay, so yeah, this is the one problem. So let me add some new problem. One second. So the second problem is limit x goes to 2, limit to x is equal over 1 plus 2t by x minus 2. So here also there is a problem here. Okay, huh? So yeah, the four as it's correct. Here also, if you put x equal to 0 by 0 form, so it will also by 0 by 0 form, right? So this will be what? This will be limit x goes to 2. Then now we use the Taylor's theorem again. To the power root over 1 plus square into 1 by 1. Now it is putting the value 2, so e to the power root over. Yeah. Now consider this problem. So let me find the problem first. Let f0 to r continues. And equals 0 to x, f is equal to integration x to 1 f for all x equals to 0. Prove that fx equal to 0 for all x belongs to 0. So, as before, so here also as before, we need to use the same trick and we need to derive it on the both sides. So what? So, yeah. So given 0 to x f is equal to x mark. So 0 to x f plus 0 to x f is equal to 0 to x plus x to minus. This will be equal to 0 to 1. Who is a constant? This implies 2 integration 0 to f is equal to 0 to 1 f. This implies what? Now doing the derivative. So 2fx is equal to 0 implies fx equals. So yeah, so this type of problem can be solved using the same method. Okay. Now, okay, so yeah, I don't think there is no point of doing more problems here. So first, so let's recall. I mean, let's revise what's the problem we have discussed today. So first, today we first introduce the. So first, today we have first into the upper sum, then we into the lower sum, and the definition is and the definition. So we introduce the fact that when a function is said to remain integral. If this holds, then the function is non-integral. Then the first problem we have done is that when a given function when the first problem we've done is that constant function is always Riemann integral. Okay, we have proved it using the we have done this integration. Then we have shown that the function this function which is zero at rational and one at rational is not integral again using the definition. Then we introduce normal partition and then one of the most important useful theorem this. First, should practice this practice problems using this theorem. Very important tool and very useful tool also. So as an application of that theorem, shown that the identity map is Riemann integral, and we find the value of the integration. Okay. Next thing, we introduce fx equal to e to the power x. So the next thing I've shown that fx is equal to exponential. I'll find the value of integration e to the fx. And so in order to we so let P in partition of P with B minus A. So then and putting H equal to B minus A by N, then to the partition P, and finally we have calculated UPNF and then calculated the LPNF, and then we found out the limit that both limits are equal to e to the B minus e to the power A. So the integration e to the power x dx is equal to e to the B minus e to the power A. So consider the function f defined as 0 1 by fx is equal to x when x rational and 0 when f is rational. So using the calculated lower integral, upper integral to be half and one 0. So f is not integral. Next we have made some we have we have stated some theorems. So model function of the integral. Second one is continuous map is always integral. Third one is function and finite number of discontinuous is always integral. So we have not proved this theorem because I believe that this proof theorem has been proved in the class, and if not, then one can go through any textbook or just one can any Google it to look at the proof of this theorem. And also we have shown that integration a to b f plus g is equal to integration a to b f is equal to b. That's the integration is. And there's one more theorem here. And finally, we have the final theorem was that if f is integral, then mod f is integral. And product of Riemann integral function is also Riemann integration. So then using these tools, we have first to show that the box function is Riemann integral. So the function f is box x. So the function on the 0, 1 is 0. So we have first split the function in the intervals, and then we found the integration first in each part, then we sum up it. Okay. Then we found the integration of fx equal to 1 by n. I mean, fx is 1 by n, 1 minus 1 is expressed as 1 by n. And it's equal to. So here we have shown that f is equal to 0, 1 and evaluate integration 0 to 1 f. So here also we have first split the function f into each of this interval, and then we found out the integration of this f and we need to of some functions different. And then we have separately calculated this small integrations, and if then we finally add it up. Now there is something called the fundamental theorem of integration. So the first thing is if should Riemann integral and pause as anti-derivative, then this holds. This is known as the fundamental theorem of Riemann integration. Very, very important for examples. So the first problem we have told is the function defined on. So this is first x squared cos pi by x squared and 2 pi sin pi by x squared. So we need to show the integration. We need to find integration, but since phi is already antiderivative, so by using the fundamental theorem, we can directly get that this value is nothing but phi 2 minus phi minus 2, which is equal to h2. Now also now we have evaluated the following limit x goes to 3 into 0 to x squared plus dt x squared. The first one is 0 by 0 form. So we had derivative. We have done derivative. So after it will be. And then the next problem is also almost the same, but it's a bit tricky. So first this condition. So after this condition, we finally get this derivative. We finally see x and f of minus x. Then the next problem we have shown that if continuous equal to 0 and either the ratio we show the same problem, the derivative technique. After doing the derivative, we get fx equal to x plus k, and given condition implies x equal to 0, so k equal to 0. So fx equal to x. Okay. And and then we have shown that the function satisfies this property you need to of function. Integration minus x to x f dt equal to 0 given. And then using the same technique, we finally showed that this is equal to 0 to x f and it is 0 to minus x. We get the minus. So if it's an odd. Then we have calculated some limits. So integrate x square sine root e x square 0 form. So we have done the derivative with L'Hopital's rule, L'Hopital's rule, sorry, L'Hopital's rule, and this is equal to x. And then it goes to it is to x to the root of 1 or dt of x minus 2. This is equal to the root 5. Same technique, just the demand, using the L'Hopital's rule. Now, if it's a function of 0, 1, 2 are continuous, integration 0 to x, f integration x to 1f. So we need to check the f(x) equal to 0. So here also we have calculated that. So first we calculate the integration 0 to x f is equal to x to 1 f. And this integration 0 to x f is equal to integration 0 to x f. So both sides we have adding integration 0 to x f. Okay. So after this is equal to 0 to 1 f. Now since it is a constant map, so this gives we integration 0 to x f is equal to integration 0 to 1 f. And this is equal this implies 2f equal to 0, so f equal to 0. So the main technical tool that we have used here is one is the fundamental theorem. This is the one thing. And another technical tool that we have used these theorems. These theorems. So yeah, so you can find this theorem in any right standard textbook. And if you have also any doubt in the questions, please ask me in the next live session. Okay. So also today I think it's already 2 hours. So I think it's fair to okay, if you have any questions in it out, please let me know. The next live session. Thank you. I am leaving the call now.